Welcome back to the Neuro Symbolic Channel. I'm Paulo Shakarian, and with me today have a very special guest, Alessandro Oltramari, and he is the president of the Carnegie-Bosch Institute at Carnegie Mellon University, and also a group manager for Bosch Research. Welcome, Alessandro.
Thank you, Paulo. Thank you for having me.
So, I got to know Alessandro over the last couple of years because he was actually a longtime collaborator of our mutual friend Christian Lubier, who became somewhat well known in the field because of the work on the ACT-R cognitive modeling framework. And today, we're going to kind of be taking a look at how that framework could be leveraged in a neurosymbolic approach, how it can be used to augment the abilities of language models for domain-specific tasks, and get ideas on sort of, what the way forward is with a lot of this technology. So, but before that, maybe if you could kind of give us a little bit of your background, Alessandro, like how did you get into AI and cognitive models? And I was actually interested also to understand because Christian pointed out to me a couple of months ago that you actually used to do a lot of work with ontologies as well, and I didn't realize that.
Yes, actually. So, my I would say journey in AI started, I think, in 2001 or so. After graduation, I had like a bachelor in philosophy of science with focus on logics. I started working with Nicola Guarino in Italy. So Nicola Guarino is considered one of the founders of applied ontology. Other relevant names in the field, Barry Smith, active in Buffalo here in the US, and prior to that it was in Germany and UK. Also Leo Obst here in the US, and many others. And so the idea of applied ontology is really to formalize word knowledge by using principles of logics, of cognitive science, and of course, using formal languages, in particular machine understandable languages, to actually make sure that these ontologies can be also consumed by algorithms and by AI systems, mostly symbolic systems. And this actually, the field of applied ontology is the field that originated the semantic web and semantic technologies in general, and the rest is really history, right? Since the very beginning, however, my main interest was on how we model cognition, how we model human understanding of the world at the machine level, so how we can replicate that. And I would say very quickly I realized that symbolic approaches, and I was fascinated by symbolic approaches, by the capability with an expressive language to describe the world. That fascination started for me in philosophy by reading a book by Rudolf Carnap, the logical construction of the world, where you actually can describe the world and the facts in the world logically. But as I was saying, I quickly realized that that wasn't just sufficient. And that's where I started looking into machine learning and combination of, back then it was called sub-symbolic methods and symbolic methods. So fast forward to, I think, 2010, I got in touch with Christian Lebier. I was looking into, an experience abroad that then, ended up in me staying in the US. And Christian had a very interesting project funded by DARPA called the Mind's Eye program. So it was the Mind's Eye program, and the project was about, creating the next, I would say, the next solution in machine vision, which wasn't just about tracking objects in space, doing segmentation or labeling, but was about recognizing activities especially I would say human behavior, looking at visual inputs from cameras. And in 2010, there wasn't any foundation model, there wasn't any LLM. The idea was really to leverage machine vision, so computer vision back then, so and integrating that with some higher level reasoning capabilities, which in this particular case was the focus of my project. And that's when I started to work on the ACTAR cognitive architecture, in particular integrating ACTAR cognitive architecture with external knowledge resources or ontologies that can describe actually how activities and behaviors emerge from a combination of short-lived actions like me extending the arm or bending over or grasping an object and put together form higher level activities like chasing someone or burying an object in the ground and so on and so forth.
Okay, so that's interesting. So when you touch on something there that I've actually been reading a lot about lately, which is the symbol grounding problem. And it's interesting that a lot of the work in symbol grounding first came up in sort of the early to mid 90s due to the dissatisfaction with some of the expert systems at the time, because the question was, hey, where does this logic come from? And then I think, to where you were in the early 2010s, looking at how to marry ontologies with perceptual data. So what were some of the challenges there that you had to overcome?
Absolutely. That's a great question, Paolo. That was the main challenge that we had to overcome, right? Because an ontology describes deterministically the properties of objects, but when you pair that with perceptual information, you are trying basically to map classes and well-defined categories to noisy information because that's the nature of perception. And that's where actually I found cognitive architectures particularly useful. When we talk about cognitive architectures, there's always, I would say, a module that includes, represents declarative knowledge. So knowledge of the world, factual knowledge that describes that, for instance, cars have four wheels, that humans have arms and legs, and they can perform some actions, but not other actions. So when you try to match this categorization of the world to specific perceptual inputs, the problem is that you have to adapt some noisy information with something that is not noisy. And so the idea is that this process can actually be performed by the cognitive architecture, different modules. For instance, ACTAR as the architecture I was working on back then as a visual module that takes the information from the world, from any external source, and carve that information into different chunks that are represented through specific properties. And this is where let's say the representation, the symbolic representation matches the sub-symbolic aspects of the world. When we think about the notion of chunk versus the notion of class in ontology, they are actually very similar. You can think of a class, again, the class of car having properties, and a chunk can be the chunk car with a sequence of different properties. However, all these properties can be, in a sense, weighted and can have different, I would say, strengths and values associated to them, which is exactly when the probabilistic properties of the world, the stochasticity of the information from perception, needs to be matched with the deterministical aspect of class representation.
So that's something that I caught on right away when I started working with ActR a while back. And I think it's quite a powerful notion because you're taking in all this perceptual data from the model and relying on notions of like recency and frequency amongst the chunks in memory, as opposed to just making a straight classification decision like traditional ML models do. I'm tempted to get more into the weeds on some of that, but I think it would be good if we took a little step back and maybe talked about cognitive models and the ActR architecture, because unfortunately it's not as widespread in people studying AI nowadays. And actually, even like if in sort of traditional stuff, I remember when I first taught AI out of the Russell Norvig book, I noticed that they're like, well, you could do AI by trying to do things rationally or trying to model things like how humans do. This book will focus on rationality, and that's kind of it. Um, so maybe it would be helpful if you gave us a bit of an overview.
Right, and maybe I can share a couple of slides for this particular topic. Let me see if I can share my screen here. Right. So this actually comes from a recent keynote I gave at the AAAI Spring Symposia. And I think, overall, the main notion behind cognitive architecture is the notion of bounded rationality. It goes back to Herbert Simon, fellow here at CMU, who is, considered one of the, of course, grandfathers of AI. And this is a very powerful notion, in my opinion, especially when we look at how LLMs these days work. They need a massive amount of training data for their predictions. And here, when we look at humans, is the opposite, right? So we have limited cognitive capacity, we have limited information about the world, we have limited time to make decisions, and so this decision under bounded rationality, with small data, with small resources, with limited time, because this comes really from our, I would say, heritage and our necessity to survive in the world. This is so powerful, and so this means that there is something very peculiar in human cognition that is currently at odds with, I would say, mainstream AI. And so when we look at this notion and translated that in the computational level, this is where cognitive architectures come into play. So they are considered frameworks that capture at the computational level the invariant mechanisms of human cognition, attention, memory, control, learning, adaptability, and so on, and perception, of course, that we just discussed. And so if a cognitive architecture is the framework that you use to replicate these mechanisms, then a cognitive model is a specific software artifact you develop to model a human task. And the human task here is very generically conceived. So I think and cognitive architectures have been around for more than 40 years. There is a paper quoted at the bottom of this slide from 2018. So it's almost 50 years now of cognitive architectures. And so, like it happened to other methods in AI. So so why didn't cognitive architectures break through? Why, if these systems are so powerful in modeling human cognition, what was that impaired their development and their success? And the problem there, I think, is the same problem that affected also symbolic AI in general, scalability. So when you develop a cognitive model, that model requires a lot of, I would say, human effort. It's still relatively heavily human, I would say, modeling task. And then when you go from task to task, then you often require to start from scratch. It's not always the case because human tasks have similarities, but that's definitely one of the features of these systems. However, recently, the common model of cognition was kind of, was a recent development that consolidated decades of research. And so the main proposers of cognitive architectures in the state of the art, I'm thinking about SOAR, of course, Actar as well, and others, came together and defined what are the minimum components that a cognitive architecture has to implement, has to fulfill in order to create cognitive models that satisfy multiple tasks. And you can see that in the middle of this slide, of course, motor models, perception models, declarative memory, procedural memory. So memories that contain information not in declarative form, but more like as rules. So if I see a tiger, I flee from the scene, and so on and so forth. And another interesting piece of the puzzle, I would say, is a paper that came out in 2021 by Andrea Stocco and others, who actually looks at the mapping between the common model of cognition and the human connectome data, showing how these different memories and different systems map to the corresponding, I would say, areas of the brain. So this, in a nutshell, and also I realized very rushed kind of summary of what is the role of cognitive architectures in AI.
No, and that was really helpful. Also for our viewers, if you are interested in learning more about the common model of cognition, particularly how it that this common model architecture aligns with human cognition. Andrea Stocco gave a really great keynote at our conference back in May, and we have a video of that on the channel. He talks about some of that stuff. So, speaking of cognitive models, though, I know there's been this recent line of research out of Germany where they have trained large language models on psychology experimental data in an effort to create a cognitive model type of system that way. So more focused just on, training on behaviors and obtaining certain behaviors as opposed to architecting a cognitively plausible model. And I know this starts to relate to some of your recent work at Bosch. So, what are your thoughts on this approach?
Yeah, so a couple of years ago, we stumbled upon this paper by Binz and Schulz, turning large language models into cognitive models. And so what was the main thesis of this paper? A thesis actually that I really embrace, right? So when you look at LLMs and their shortcomings and their problems, what you observe is that they make horrible mistakes, they hallucinate. No matter how much you train them, I've seen example about GPT-5 still making very silly mistakes on counting letters in a word and so on. So they seem to be alien intelligence in the sense that they exhibit features and problems that toddlers don't have, right? And so the thesis of the paper was, how do we make these models closer to human cognition? And so the author said, well, we have a lot of data from cognitive psychology, years and years of behavioral data that describe performance of humans in several tasks. And so since we are already quite familiar with the mechanisms of fine-tuning general purpose models for specific tasks, why don't we do the same with behavioral data, and with the intuition that this would make these models behave closer to humans in these cognitive tasks? And so they proceeded by using a open source pre-trained language model. I think it was Llama 65 billion parameters. And in this fine-tuning, I think they call it Centaur, to predict basically human decisions across various domains. And they actually show not only that the model was performing on par with humans, but in some cases, in unseen tasks, they could see a transfer of these cognitive capabilities of the model. And so that was very interesting for us. And why, right? So, well, there are many tasks that we see in our work at Bosch that deal with manufacturing. I didn't provide an overview of what Bosch does, but I think the viewers may know that we cover a broad spectrum of product and services, from automotive, power tools, home and so on, home appliances and so on. And so all these products, of course, require, I would say, a pipeline of production, and we have different plants that operate at different levels. And so many processes and that we see in our plants, where humans, of course, control different machines and work on production, optimization of production, and so on and so forth. So in general, and this is not just Bosch, this is just any company that focuses on, I would say, hardware, and in any case, mechanical engineering. There are a lot of tasks that we do that can be augmented by AI. But in a framework where the humans is still so humans are still the ones that make decisions, it's important to focus on human-machine collaboration rather than delegating completely decision. Also because, of course, it's a very sensitive domain, and as we see shortcomings in question answering or other general tasks dealing with language, the problems are also translated into the physical world, even worse there, right? So we thought, well, maybe we can see if we can follow the footsteps of Beans and Schultz and fine-tune a language model, to help a human operator in the plant in the different decision-making processes that they go through. The problem is that in the plants, we don't have the same amount of data, of human behavioral data, that Beans and Schultz could find in the cognitive psychology literature. And that's where we started thinking about using cognitive models of these specific tasks in the manufacturing facility to create synthetic data at scale that we could use to fine-tune the models. Now, of course, this only works if the cognitive models that you create are able to replicate with high fidelity these human decisions and processes in reasoning that we observe in the plants. And that was, I think we published that paper a couple of years ago. We showed that our fine-tuned model was performing much better than the baseline pre-trained model, unsurprisingly, of course, in those specific tasks. And so we started that line of work. There are several limitations. The limitation is that we focus on a couple of tasks that are very self-contained and very specific. And so we don't know how that would scale in the future. And in general, yeah, I think our results and our methodology also open up a different discussion, a discussion that I think is still open, and it is, what does it mean to fine-tune a model in terms of the reasoning capabilities of that model? Because at the end of the day, if we think that human reasoning is something that emerges from a combination of knowledge, a combination of cognitive mechanisms, and grounding in the experiences of the world, then the mechanism of fine-tuning, which is very much like training, doesn't add any capability in principle to the specific, I would say, internal mechanisms of machine learning. And so why are we expecting better reasoning if we are only providing more data for the model to kind of, enrich its own latent semantic space?
So, I mean, a couple of questions on that. So when you say fine-tuning, are you're doing supervised fine-tuning of the model, or are you doing something with like RL?
No, it was more like a supervised. Although we also thinking that, as we see in the literature, RL would be a powerful mechanism to add into the system.
So on the supervised side, do you think there's like a limit as to how much supervised data you could synthetically generate with some of these models and performance? Like, does the performance level off somehow? And then likewise, is there, I don't know if you studied this, but do you think there are equivalent performance curves? So, I don't know, let's say like, uh, 10 terabytes of synthetic data is from the cognitive model is maybe as good as like 1,000 terabytes of data just from the web or something like this.
This is something we haven't studied, but it's definitely interesting to try to understand, I would say, how the different features of the generated data match, and what is the ratio in a sense in terms of getting to the performance that you would require. So definitely an interesting aspect.
So getting also to your comment about like, what is fine tuning? Why would you think that just the use of data from these synthetic data from these cognitive models, would not be enough to improve performance or improve performance beyond so much? Do you think it's like due to architectural limitations or the fact that, it's like a lot of people, especially in the neuro symbolic community, say, well, like there's no real reasoning going on. It's just kind of, doing this autoregressive thing.
Yes, yes, and we've thought about that a lot. And well, maybe one thing that I can say about the data that we use for fine tuning, I would say this is not just, I would say, the results of the decision processes that we are feeding the models with, the large models with. We try also to incorporate elements of the trace of the model. And for the viewers, the trace of a model is the output of a cognitive model running and simulating again these decision processes. And what this trace contains is at a, I would say, very fine level of granularity, what modules of the model are used, for instance, the declarative model, the procedural model, what type of sub-symbolic mechanisms are used to compute, let's say, what is needed for the decision. So, given a situation, the model translate that and maps that to the declarative memory, and then typically, again, this is just a simplification, typically it would also call or trigger a set of rules that are needed to make the decision. So we try actually to incorporate in the data all these sequences. And of course, in order to do that, we need to adapt the trace of the cognitive model with the expected formatting and nature of the data that are required and instrumental for the fine-tuning. And so, in a sense, our weak hypothesis is that by providing these signals that tells the model this is how a human makes his decision, we are also giving something more than just the final data that represent the state, the final state of the decision process. But I would say the following. This is a limitation, an intrinsic limitation, which we observed also in a previous work that we did by fine-tuning models, so large models, with common sense knowledge bases to improve their performance in common sense question answering tasks. And what is the parallel? Similar to what I've just described for cognitive models, we have seen that when you have a question answering tasks, a famous one used to be a common sense QA, CSQA, I think it's still in benchmarks. And so you provide knowledge from, so common sense knowledge from resources like, I don't know, WordNet, FrameNet, or supersets of these knowledge bases like CSKG, the initiative led by Philipp Ilevsky. So these models perform better than just the pre-trained off-the-shelf model, but still they make errors in reasoning. We see errors in temporal reasoning, errors in spatial reasoning, errors in analogical reasoning, metaphorical reasoning. All these different reasonings that have been studied profusely in the literature. So what we observe is that the knowledge of the world, the common sense knowledge we could find to fine-tune these models wasn't sufficient to kind of cure these models from their hallucinations and mistakes. And so similarly, when you use these synthetic data from cognitive models and fine-tune LLMs, you are not curing them from those same issues, and you are not inducing any high-level cognitive reasoning yet, because, and this is the thesis that now we are working with, you need something more to capture that aspects of reasoning, which is, I believe, what neurosymbolic approaches in general are good at and are showing, how to do that in different ways.
So that's kind of interesting. So when you feed the synthetic data to the LLM, is it all in natural language, or because since you're giving the trace, are you converting it to all natural language, or are you having it in some kind of ontology?
Yes, is a kind of controlled natural language, if you want, yes.
Okay. I mean, because part of me wonders, thinking about like kind of Alpha Evolve that was released earlier this year, where the language model was used for candidate solutions, and verifiers could take a look at the result, and
Yep.
In this way you could guarantee correctness of the reasoning. Do you think something like that could be possible in this domain?
I believe so. I didn't actually think before of something along the lines of alpha geometry, for instance, also as an improvement or as a direction for our work on cognitive LLMs. But I've been a fan of that type of approach since the beginning. And for me, the beginning, at least in my own experience, was when I read this paper. Gosh, now I can't remember the name of the first author, but the paper is called Road R, and was about using rule-based reasoning to basically clean up predictions from a computer vision model that was looking at, let's say, autonomous driving kind of data set, where, in some cases, the model, so the vision model was predicting that the traffic light was at the same time red and green, which of course is impossible. And so this rule-based reasoning at the end of the pipeline was used to exclude some of those, let's say, hallucinations or contradictions in many cases, and clean up a little bit the classification of the scenes. And so alpha geometry is similar, right? So you have a symbolic reasoner or verifier that looks at a bunch of different proofs generated by the large model and clean up the mess, so to speak, so that you end up with the results that are sound and accurate. And I think this is a very valuable approach and a very, I would say, promising combination of symbolic reasoning and machine learning at scale.
I would agree. Do you think in looking at that, do you think the natural language piece adds a level of difficulty to using a verifier or something like that to clean up the results?
Uh, I think it definitely has an intrinsic level of difficulty, um, which is, I would say, um, really linked to the complexity of language, right? So, but a good friend of mine, Sergei Nirenberg, has been working on this for many years now, right? So, I think the type of approach where you can have a very well-defined system that um, combines different natural language understanding algorithms. It's what you need at the end of this pipeline, where the beginning would be large models. And I think Sergei's group has, showed very interesting results in that perspective. Again, the problem is, how are these neuro symbolic system are they scaling? Can you scale them? Can you apply them and get runtime results like you get when you chat with ChatGPT? And that, I think, is still to be seen.
No, I think that's a fair point. Maybe kind of as we move toward a close, can you you talked about how this work is relevant to things, systems used for industrial work and the domain knowledge that goes into that, while at the same time not having a lot of samples, which is kind of the genesis of this. How does this relate to kind of the portfolio of research going on at both Bosch Research and the Carnegie-Bosch Institute as a whole?
Right. Let me maybe first, make a distinction between the two, right?
Yeah.
So Carnegie-Bosch Institute, as I maybe mentioned at the beginning, it's part of Carnegie Mellon University. So it's an institute that was created by Bosch 35 years ago through an endowment at CMU. And the mission of the institute is really to promote synergies between academia and industry. And we do that in a variety of ways. We run a successful postdoctoral fellowship program. We sponsor some research within CMU, or we synergize with CMU faculty to work together in project proposals and so on and so forth. So from the standpoint of CBI, so Carnegie-Bosch Institute, I must say that we have seen over the last 3 years a lot of interest in working on improving LLMs, or in general, I would say, foundation models in terms of reasoning. Okay, and one example of that is a former postdoc, former because I think he just is now, I think as of August, a part of the faculty of the University of South California, Santa Cruz, I think, Xiang Yue. So when actually he joined the CBI, he was acknowledged by the Google Gemini white paper for the benchmark dataset he created to test multimodal reasoning in models. And so we have seen that as an example, but we have other postdocs and other interests that we see in faculty in the area of Neuro Symbolic AI and reasoning in general with LLMs. And now, this from the side of CBI, right? From the side of Bosch, and this again, I think it's true for many, I would say, large scale companies that we see in the world. There is a lot of domain knowledge that has been, I would say, collected and I would say piled up over the years in different formats, from spreadsheets, databases, knowledge graphs, ontologies, knowledge that is not easy to extract. So the tacit knowledge of the human operators, for instance, that you need to observe as it's in its action. And so all this knowledge is there and is very useful to bootstrap some of these technologies based on AI that we are developing. And so again, the combination of knowledge and data-driven algorithms, it's very important for industry in general. And my I would say prediction is that it's not going anywhere. I don't think Neuro Symbolic AI will see a slowdown, especially for industrial applications, because it's too important to make sure that when there is valuable knowledge, that is used together with AI technologies.
No, I think that's an interesting take. What are your thoughts, though? I mean, you mentioned that all this knowledge is kind of strewn all over the place in many different formats and stuff. Do you think that that's an impediment to progress, or is it something that people will just start figuring out different ways to translate these into common systems?
Well, it's not, I would say, an obstacle per se. It does require the machinery in place to kind of, I would say, make this knowledge more homogeneous and kind of consolidate the representation when there is a representation. Because of course, domain knowledge, when we think about domain knowledge, can be of any type, right? Can be a spreadsheet, as I mentioned, a knowledge graph, can be a circuit diagram that is also knowledge, right? And then how do you put everything together? As a matter of fact, people are already using multimodal large models to take all this information and create summaries, distill, I would say, homogeneous representations. But then, of course, that becomes a chicken and egg problem, right? Because if these models are making mistakes in this consolidation, and then you are using the result of this consolidation for the rest of your AI pipeline, you may end up in, of course, systems whose predictions are, kind of impaired or are poisoned by problems in all these different stages. And so that's where I think there's also more room for symbolic methods to be effective and efficient for the future of AI, because I think there is still a lot that can be done in terms of semantic technologies and in general consolidation of knowledge under the general ontological models to bring together different formats, to bring together different sources of knowledge and represent them and make them fruitful for AI in general. There's a very important, I would say, NSF program called the Open Knowledge Network, which in a sense is looking into that direction, right? So how do you federate and put together different resources, and in some cases translate what is not structured or formalized into a more structured and formalized format that can be used by AI models.
Oh, that's interesting. It makes me think of the old work by Psychor and Doug Lenat when they tried to formalize everything.
Yeah,
Well,
and
I think, go ahead.
if I can add one thing there, I was last February there was a workshop at AAAI, the TICA, that was exactly looking into what do we need to do in symbolic AI to meet the challenge that neural models are actually putting in front of us, right? So the challenge being, we need to ground these systems, but we also need to provide these systems with knowledge at scale and knowledge that has high quality representations. And psych came up many times in that workshop, and in fact, we had also people from psych because that was the quintessential endeavor to formalize knowledge. And so the idea is that what is next? As I think this is a very important research question for the community, and of course we need to see what the answer will be. But I think again there is a lot of interest these days, and to be fair, I think this interest is also the result of a new wave of AI interest and AI, I would say, investments thanks to large models.
No, I think that's an excellent point. And probably a good one to close out on, actually. Anything else you want to add before we wrap up?
Not really. I just wanted to thank you again for the opportunity to share a little bit of my research experience and work. And also, it's interesting because every time you have a conversation of this sort, there are many other conversations that you would like to have to deepen more and more, these topics. So, thank you again for the opportunity.
No, thank you. And thank you so much for agreeing to join us today. And to the viewers, thank you for tuning in and supporting the channel. We will have some links to more information about Alessandro and his work and Bosch Research and Carnegie-Bosch Institute in the description. Don't forget to like and subscribe, and thanks again for tuning in. Take care.
Thank you. Bye-bye.